Hi everyone, so welcome to the final, the third phase of your three-phase systems review. And today I hope you will be able to derive the three-phase power equation from the single-phase power equation, and you should be able to also calculate P, Q, and S for three-phase loads. Now, just like single-phase systems, three-phase systems AC, and the equations are the same, except now you have three phases instead of one. So you just add up the phase powers and you get the three-phase power. It's as simple as that. But since we usually have line parameters to work with, which we don't have in single-phase systems, remember, line parameters means line to line. There is only one line in single phase, so you don't have that. You just have phase voltages and phase currents. Since we have line parameters in three phase, and these are the ones that are usually used, then it's useful to derive the power in terms of these line parameters. So just to recap, we know that the power per phase is V phase multiplied by I phase by cosine theta. Be mindful that these are the absolute values, they're not the phasor values, and cosine theta is the difference between the phase, difference between the angle of the voltage and the angle of the current. So what we want to do is we want to replace basically the phase values here, the phase parameters here with the line parameters. So for Y configuration, we know V phase is equal to 1 on root 3 by V line. Remember, there's no angle here because we're just looking at the modulus, the absolute values, and we know that I phase is equal to I line. The magnitude of I phase is equal to the magnitude of I line. So the power per phase, if we substitute V phase, is 1 on root 3 V line to line. We will get this part here, and then I phase is equal to I line. We get this part here. Cosine theta remains the same. If we do it for delta configurations, we know that V phase is equal to V line to line. Remember, we have this equivalence between the voltage on the delta and the current and the Y, and conversely we have the equivalence between the voltage on the Y and the current on the delta. So if we substitute the values now for phase voltage and phase current into the equation, we get V, this should be magnitude here, V phase is equal to V line to line, and I phase is equal to 1 on root 3 I line. And if you look at these, you'll realize they're exactly the same. So whether we have a delta configuration or a Y configuration, the power is exactly the same if we write it in terms of the line to line values. Note, and this is very important, the power factor angle is still between the phase quantities. So this theta here, we didn't substitute that. This theta is the same theta that was here. So it was not substituted. It is still the difference between the phase voltage and the phase current. So keep that in mind. Because remember, if we go from delta to Y, one of them, either the voltage or the current will be shifted by 30 degrees. So you don't want to mix up what your use a line current instead of a phase current, and then something gets shifted by 30 degrees and it throws off your power factor. So it's always, the power factor is always considering phase quantities, not line quantities. And similarly, we could derive for the reactive power, and it's the same equation except we have sine theta. Remember, from your power triangle, we have P and Q. So we get cosine theta for P and sine theta for Q. So for three-phase power now, it's simply 3 times the single phase power. So remember, the single phase power was 1 on root 3. We multiply that by 3 and we get 3 on root 3, which happens to be root 3. So root 3 V line to line, I line, cosine theta is our 3-phase power. And the same thing, but with sine theta, is our reactive power. And if we want to get the magnitude of the apparent power, we simply use Pythagoras' theorem and we get root 3 V line to line, I line. This is the absolute values. These are just magnitudes. They are not the vector quantities. They're not the phasor quantities. So let's look at some examples. First off, we have a 3-phased balanced Y delta system that has a line voltage of 208 volts. The total real power absorbed by the load is 1200 watts. And if the power factor of the load is 20 degrees lagging, determine the magnitude of the line current and the value of the load impedance per phase in the delta. So we have a Y source, and that is driving some delta load. This is driving some delta load. And we know the line-to-line voltage is 208 volts. And the power P 3-phase is equal to 1200 watts. Power factor 20 degrees lag. So this is the information we have. So what we need to do is we need to find what is the power per phase. So if this is a balanced system, which it is, then we know the power in each one of these is equal, and we could find the power per phase, which is 1200 divided by 3, 400 watts. We know now from our power equation, which is P is equal to VI cosine theta. I actually have it right here. P is equal to V phase I phase cosine theta is equal to 400 watts, which is P phase. I substitute the values. 208, which is my line-to-line voltage. This is my line-to-line voltage, but we said it is the phase voltage we need. But remember that the phase voltage, which is the voltage across here, is the same as the line voltage for the delta. So in this case, V phase is equal to V line. So 208 multiplied by I phase multiplied by cosine 20, which is the power factor angle, the angle between the phase current and the phase voltage. So I have 400 is equal to 208 I phase by cosine 20. I could simply solve for I, and I get 2.05 amps RMS. That is the phase current in the delta. If I want to find the magnitude of the line current in the delta, I simply multiply it by root 3 and I get 3.54. Remember, the line parameter is always the one that is larger. So I line root 3 by I phase 3.54. Now I need to find the value of the impedance. So value of the impedance, V phase over I phase, is going to give me the magnitude, and from my cosine 20 degrees, which is my power factor angle, that is the angle of the impedance. If you can't remember why that is the angle of the impedance, just remember we could look at some impedance block here, and if we have some Z angle theta, and we have V angle theta V, then I, make this theta Z, I is equal to V on Z angle theta V minus theta Z. And remember, the power factor angle is the angle between the voltage and the current. The angle between the voltage and the current here is theta V minus theta V minus theta Z, which is simply theta Z. So the power factor angle corresponds to the impedance angle. So to get the magnitude of the impedance, V phase on I phase, because remember the impedance is the phase impedance, and then the angle is given by the power factor angle. Second example, we have a balanced three-phase system, a balanced three-phase source which serves three loads. These are three-phase loads, not three single-phase loads, one on each phase. It's three-phase loads. One 24 kilowatts at 0.6 power factor lag, 10 kilowatts at unity power factor, 12 kilowatts at, this should be, sorry, kilowatts at 0.8 leading power factor. And if the line voltage is 208 volts at 60 Hertz, determine the line current and the combined power factor of the loads. So we have the three powers, and we simply add them up just like we did with single phase. If you have a number of loads in your single phase AC question, you got the real and the imaginary, which is the real and reactive powers, and we added the real, we added the reactive, and we get the total power. We want to find the line current. So here the line current, we know this should be magnitude here. We know the magnitude of S is equal to √3 multiplied by the magnitude of V line by the magnitude of I line. So we could find the magnitude of I line by simply substituting V line and S. We know S here, the magnitude. We know V was 208 and we have our √3. So we simply substitute and we get 139.23 amps. Power factor again is simply the power factor angle here, the cosine of the power factor angle, which is the power factor at the power factor of the combined load. Third example, using the same three-phase system, assume now we have a line and the line impedance is given here, and find the source power factor and the source voltage. So we have a source and we have a three-phase line here now with some inductance and which is some RL circuit, and it is connected to the same three loads. It is connected to the same three loads. So how we would do this in our single phase system is we would find the combined power, find the line current, then multiply the line current by the impedance, get the voltage across there, and then we have the voltage and the current, and we could compute the power. We're going to do it a little bit differently now. We could still do it like that. There's no problem in doing it like that, but we're going to do it this time by finding the power instead. So either way is okay. So we have the power dissipated in the line is 3 times, because there are 3 lines, one for each phase, IL squared. Remember, IL is the line current by the line impedance. So we have I squared Z, which is the power, multiplied by 3, and this is the result we get. So we simply add this power, which is the line power, to the load power we already calculated, the aggregate load power, and that gives us this value here. Now if we want to find the magnitude of the source voltage, again we just have S, this should be magnitude here, and magnitude here. We know that the magnitude of the voltage is S on root 3 IL. So we have IL, it was, if we go back, 139.23 amps, that was the magnitude. We have the magnitude of S here at the source, so we could calculate the magnitude of the voltage. And again, the power factor at the source is simply the cosine of the angle of the apparent power. Good. So in summary, we looked at the derivation of three-phase power from the single-phase power equation, and we looked at calculating P, Q, and S and the power factor for three-phase loads. This brings us to the end of our review of three-phase systems. Again, all of these things are things you should have done in ECNG 1015, so nothing here should be new. And we will get started with the new material, looking at transformers in the next module.